what he said. All right, so this is the, okay, so Favoni, I guess, put these up, so please get your homeworks in, and homework 2, and I didn't look the notes from last week, or, well, week before, logically not last week, those are up? The previous set of notes? They are? Okay, I didn't look actually yesterday. All right, I want to make sure we're keeping up on the note taking. Okay, good. I'll erase. Okay, so what I wanted to do is so where we are is we have developed, so far we've developed what we call intuitionistic propositional logic, which I've written this many times on the board, but I'll just summarize it again. So we have the propositional connectives, and we studied their behavior, A implies B, and we gave them, see, I'm already doing it, I can't help it, it's too burned in. Okay, and then you have a corresponding sort of, type notation for these things, and we were looking at their properties that we developed here, and what I said to you last time is the propositions as types correspondence tells us that we really don't, what I was trying to develop with you is that we don't make any strong difference between these two. It's just a matter of point of view. So what I wanted to do today was put in a type nat of natural numbers, which doesn't seem to correspond very much to anything propositional, but that's okay. And then that is going to broach some subjects of equality, and that will allow me to begin to make the transition to talking about equality or identity at a particular type between two terms. We're going to look at that, and then there will be some other apparatus, and it's going to take a while for me to really get everything down, but I'm going to start broaching that subject. So I need a little more material, okay, here in order to work with, in order to start developing these ideas that come up next. So that's the plan. Okay, so the thing I want to mention, so what I want to do is this, I called this thing Gödel's T. Well, that's like an abuse of notation. It's not exactly what Gödel did for T because he didn't consider sums and products. It was really function spaces and natural numbers, but it's close enough for government work. So we'll go with that. Okay. So don't take too seriously like the name I give it, because if you look in the literature, it won't be exactly what I said, but it's morally kind of the same thing. Okay. So the idea is we take these are called sort of simple types, and this is a particular thing in the natural numbers. So you'll notice that the only thing I want to say is that if I throw in the natural numbers, somehow because of the identification of propositions as types, the fact that we have implication means we also have types like nat or nat, because implication corresponds to function space. So it was sort of immediate. If I do sort of something propositional and add this in via this correspondence, I start getting richer and richer type structure. So as soon as I add in natural numbers, I can start expressing some fairly, quite a lot of ideas. So the way we're going to do this is that with the natural numbers presented, I'm going to present this as in our syntactic notation first that we use. The idea is that this is the premier example of an inductively defined type, unsurprisingly. And so the way we're going to do this is we're going to define the introduction rules for this. So I'll have like 0 is going to be a nat, and I'm going to so we always do these things in unary because it stresses the inductive structure. So successor of this and that. So we can write it like that. So these can be thought of as the nat introduction, 0 and successor. Okay, so there are two rules there. And then the question is, what is the elimination form? And the elimination form is just definition by recursion over a number. You could think of it as a for loop or something like that. So what we do is we say, if I have a natural number, and I have a way of computing, let's call it, I think I call it P, which is going to be of some type A, and given something of type A, I have Q, which is some type A. Then I have something called the recursor, which it ends up being kind of convenient to write it in this funny notation, sort of curried notation. It's kind of convenient to do that for reasons that will come up later, is A. Okay? So this is the idea. So the intuition about it is that, as you probably have already guessed, you can think of this as sort of the basis, and you can think of this as kind of the inductive step. And in fact, we're going to develop that a little further once I start going lower on this chart. That will need to be amplified. This rule and this discussion will have to be amplified. But for the time being, in the setting that we're in, this is the right way to phrase it, I think. And so the idea is that you're going to compute something of type A out of, or in terms of a given something of type nat. So as I was saying last time, I'm not quite sure if I use this terminology, but anyway, we were looking at, this is an example of a positive type, something like sums, and it's positive because it's sort of characterized by a mapping out property. That is, I tell you that if you give me one of these, I tell you how to map out and give it this this behavior. So we have this thing of arbitrary type. So what we do is we just need, in order to map out of nat, I need to tell you what to do on 0, and I need to tell you what to do on the successor as a function of whatever you do on the predecessor. So that's what's being expressed here. So this is kind of like A arrow, A arrow, A arrow, A. Okay, something like that. So you can kind of think of it like that. Okay, so those are the basic syntax. And then if we look at the uses apply Genson's inversion principle, which tells us that the elimination should cancel the introduction. Well, there are two introductions, so I guess there are going to be two beta rules for that reason. And they will say, and I'll just write them in the short form. I won't write down all of the syntax, all of the judgment. If I have rec PQ, and if I run that on 0, that should be definitionally the same as P. Okay, really I should be writing in a context and what its type is in any way, but especially with the beta rules, they're really just based on the shape. You just look at this elim following intro, and then you just cancel in the appropriate way. And then the other thing is that you say if rec PQ applied to, let's say, successor of M, or I could do this with a variable, is going to be you make the recursive call on M, and then plug that in for, I think I called it X in Q. All right? So those are the two beta rules. So this allows us to sort of, so that is, so if we notice then, for example, if we write, n bar is, the n-fold successor on 0, so that's the numeral n. So then what we get is that if you look at rec PQ on a numeral, then definitionally, what is that going to be? Well, it's slightly awkward to write it, so I'll cheat in my notation. It's essentially Q of Q of P, right, for the exact same number of times, right? There's n of those, okay, maybe 0. Okay, I'm really cheating. What I mean is an iterated substitution, but it'll look really ugly if I write it out like that. So just let me write it like that. Okay, so that's the idea. That's the sole thing. It just says iterate something n times starting here and incrementing there. And then you can look at also a kind of unicity property, which is a sort of an eta thing, which was not actually considered by Gödel to my knowledge, but makes perfect sense in this situation. So here, like we did last time, we say, well, suppose we have some map M out of nat, which is expressed by an open term with a free variable z. So this is a mapping out of nat into A. And let's say it looks like a duck thing. If it behaves like the recursor, it is the recursor. So what does it mean to behave like the recursor? It means that, suppose we say that if I plug in 0 for z in M, let's call what I get out of that P. If this is the case, and then let me write it over here so I'm not bending too low. And as a function of, let's write it z here, it's convenient to write it like that. If putting in, successor of z for M, so M on the successor, if that turns out to be the same as M for X Q, right, because that's what's going on here. Think of this guy as being my M here, then it's M for XQ essentially is what's going on here. That's what's on the right hand side. So if that's the case, then what do we know? That relative to Z, we will have that M is the recursor PQ, and I can write RPQ of Z. Right, write it like that. So then it ends up being the nice way to do it. Okay? So that's it. That's what you would have for the eta rule. So it's this, again, this idea of expressing the unicity by saying if it has the same behavior, if it's the same sort of animal as this one is the best one, so to say, and so they're all it's a uniquely given map. I'll write it diagrammatically to make this clear in a moment. The rec is a uniquely given map out of M given by this data. So if something else is a map like that given by that data in the right way, then it is the recursor. Okay, so that's the idea. So there are two special cases of this, right? If you look at one of the special cases with the recursor, is worth pointing out, is that if you, let me just write Z here. If I do on the recursor 0 and let's write it Y, successor of Y, S of Y, and apply that to Z, that should be the same as Z in N itself. Okay, like that. I guess I'm capitalizing this, so let's try to be consistent. Okay, so it looks like that. So that's a special case. You just work that out, I think, if I did it correctly on paper. So the M is a variable now, just Z by itself, so 0 is equal to 0, and successor of Z is equal to successor of Z if you just plug it in, because that's the successor. And so we get that. So that's like one special case. Another one that's worth pointing out, and it came up also last time, was what is called a commuting conversion. This is an example of, in proof theory, it's called a commuting conversion, which comes up with that. And it's a little awkward to write, but, well, that's the way it is with positives. As far as I know, whenever you're writing down the positives, every damn thing it starts becoming complicated to write down. It's not conceptually complicated, but it's hard to write it down. So if we take that thing there, so if we look at, for example, rec Z and 0, Y, S of Y, this is one case of it, okay, and we're plugging that in for Z in M, that's the same thing as, okay, putting the recursor out, and then in each branch doing what you might think, which is plug in 0 for Z and M. And you can do a generalized form of this, but anyway, I wanted to S of Y for Z and M, if I'm right. So I'm pulling what I'm doing is, this is called a commuting conversion, because somehow what I'm doing is, if you think of this as substitution as composition, then what I'm saying is I can pull the composition inside I can put the M and the M here, okay, inside the branches of the recursor if it's the same on both branches on the outside. And you can do a more general form of this, but anyway, this is an illustrative example, and this again is a consequence of the eta rule if I wrote it down correctly. That should be the case. Okay. So that's so that's what I wanted to say about that. So there's some similarity, which is the reason I brought up disjunction and sorry, yeah. Mm-hmm.
Sorry, when you write y dot s of y.
Did I make a mistake? Or?
No, I don't know. Well, I don't know. When you write y dot s of y, so
yeah.
For example, in a special case.
Like here, you mean? Or?
What does that mean?
Oh, S is the successor. That's just like my notation.
So when you juxtapose it with y.
Oh, so in my syntax notation, y is a binder. And so like, let's go back over here. Oh, this should have said x.q way back when, and that's what confused you, because that's what confused you. When I first wrote it down, I wrote down the wrong thing. I left the free variable hanging. Okay, so, and then that subsequently screwed everything up. So sorry about that. Yeah.
It has 3 arguments.
Yeah, sorry about that.
In this community.
So I was using it properly here, I believe. Okay.
When rec has 3 arguments.
What's that again?
So you didn't do it the correct way.
Oh yes. Oh, and then I'm totally inconsistent about that as well. Yes.
It's right there.
This is here. Here it's not. I'm sorry about that. The reason is when I write the diagram notation. Excuse me. When I write the diagram notation, which I'm going to do momentarily, it ends up being convenient to curry it like that. That's why I did it. Excuse me. So there's a bunch of there are a bunch of notational conventions, and so I get confused about which one I'm using at any moment. Okay. Anyway, sorry for that. Okay, so that's the idea. I mean, there's not that much more to say about it. The only thing to say is that this can be here. Let's just look at this diagrammatically. By now, I hope it starts to make sense to you to write it using the diagrams because it's a nice way to, it's a nice notation. I mean, that's what I'm doing here. So the way we can express this is that we have a constant. So usually when people are saying, so this is the notion of what is called the natural numbers object. In a category, what it means to be a natural numbers object. So you have a natural numbers object, n is a natural numbers object if it satisfies these requirements. That is, well, we can call it 0 and successor. I called it S, so let me call it S. So we have 0 and S. So we have two maps, so a constant that has, no variation in its domain, and a successor which goes from n to n. So that's the first part of the data. And then it has the characteristic that if you tell me what to do on the base case with some type A, that's the A over here, so let's call that P, so this is my basis, okay? If you tell me what to do there, and if you tell me how inductively to take a step, how to go from the result on the predecessor to the result on the successor, so you give me those two bits of data, so this is my x.q in the syntactic notation over there. Then you'll be not surprised. There's a unique map which makes that square commute, okay? And what is that unique map? Well, the unique map in question is the recursor. So now this is why I ended up with that notational inconsistency, because when you write it with diagrams, you don't use variables. You think in terms of these maps, and so then I didn't write it as an x.q. So sorry about that, but that's why it happened. So this would be called rec pq. Okay, so this is what is there, and then this is unique in each case. I'll just mark that as unique. So what does that mean? It means that here's a beta step. If you go 0 and then then the recursor, in other words, you feed 0 into the recursor, then you're going to get p. That's the base case. And if you take the recursor, well, I can do it this way. If we feed the successor of something, so think of anything at all x coming in here. If you feed me the successor of that thing into the recursor, that will be the same as recurring on the thing you fed in followed by q. So if you think about that just for a second, so just say this is sort of, n. Think of it, I'll just write it n here just to be illustrative. But I have something coming into n. So if I look at the recursor on the successor of n, that's going to be the same as the recursor run on n substituted for the argument to q. And that's what I said here, modulo possibly in the eta rule here. And it's a unique such thing. So in other words, there's essentially another beta being expressed here, and then I would blow it up, okay, and put edges here. If I had some other m which satisfied the same commutation requirements, the same beta condition, then this cell here is eta, and eta expresses that that's the unique such map, that those are equal. Okay, so that's the same. So that's the same sort of thing we did with for example, the disjunction. Okay, so that's just the way in which one writes it down using diagrams. So you know that. So that's what that is. So again, the picture I want to bring to mind is that their beta conditions are these equations, and the eta conditions are sort of a combination of the universality, the fact that you can find this mediating map, and that it's unique amongst all such things. It's the best one. And so there's an eta reduction that witnesses the unicity, okay, that's going on here. Okay, so that's the idea of a natural numbers object. And I want to mention, because it'll be useful a little bit later, so reorging the NNO condition into what is called an initial algebra. So it turns out this idea of being a natural numbers object is an instance of a more general thing. And so the idea is the following, is that I can reorganize this data in the following way. I can say, I can look at 1 plus n over here, and I look at n over here. Okay, this is another way of doing it. And if you look at the universality conditions that I gave you for plus, any map from here to here must have the form of a case analysis, which I think I wrote with curly braces, and which has a branch for 1 to n, we'll call that 0, and a branch for n to n, we'll call that successor. So so what we can say is that another way of saying what a natural numbers object is to say I have such a map, which can be taken to be of this form by the uniqueness of maps coming out of plus, maps out of plus, with the characteristic that if I take any other such thing that looks good like that, where it's of the form, I've been calling it P and Q, which is the basis. It goes from 1 to A and A to A, because remember, this is case analysis, right? The curly braces is case analyze, and on the left case do P, and on the right case do Q. So it consists of 2 maps, one from A and one from A to A. So all I'm doing is I'm just re-parenthesizing this diagram. Then what you say is that there is a unique map here, okay, which is going to be, as before, the recursor, rec PQ. Write it like that, such that this diagram written like that commutes, and you write here 1 plus rec PQ. And that's, I have to define what I mean by that, okay? But intuitively what it means is, 1 here means the identity, so I could write that as identity. Sometimes people write 1 for the identity map just because they do. And so that's the identity map from 1 to 1, which I was writing as 1. And this is the recursor from n to a. Okay, so that's what is being said here. And if you work out what it means for this to hold, for the beta condition to hold, that is the commutation condition, okay? So let me just do this, is that check that this is equivalent to the previous definition. In other words, I haven't done anything, I've just reorganized it. So the beta condition is the commutation. So you can just check by doing some calculation, and I have to define what do I mean by f plus g, okay, going from, in general, a plus b to a prime plus b prime. Let's say part of it is write down what that must mean. Okay, it means case analyze on this, do f on a, and stick it in the left part, do g on b, and stick it in the right part. So you can write that down. Okay, so define that. Okay, and then check that you're getting the right behavior. So this picture, the reason I reorged it into this picture is because this is an instance of a more general phenomenon, where what we have is the general phenomenon is some kind of function that actually will be called a functor. So this is it has the form f of n, or f of, let's call it I for the initial one, down to I for various f's. So we have a particular f here, 1 plus n, and then this is what is called an initial algebra, because if you give me any other one, f of a to a, like that, then there's a unique map here, so we'll write that, and this will be f of that. And that's the general notion of an initial algebra for f, and this is called an initial algebra for f. And all I'm saying is the natural numbers is a particular natural numbers object defined sort of ad hocly is an instance of the more general notion of an initial algebra for a functor, or in particular this particular functor, which I spelled out literally here and asked you to work out just like by itself. Okay, so it's worth knowing that way of thinking about it, because lots of other stuff, it's hard for me to know exactly what we're going to emphasize in a month's time, but it might be useful to have that picture fixed in your head, okay, so that it's familiar. One direction I might go might end up involving discussing more about inductive types. So I wanted to bring that up. Okay, so that sets up what I called Gödel's T. So that sets us up for now a discussion which is preliminary to what I need to do to talk about families of types and dependent types. So that's what I want to do next. Okay, and I have enough machinery here. Oh, before I do that, I should mention a couple of things. Yeah, it'll be worth it. For those of you who are not experienced with this kind of thing. Let me make sure, we're going to give you homework assignments for this, but let me make sure we can do things. So we can define, let's just, so now I'm playing with the natural numbers with the recursor just for a second in order to set up a few ideas that I need in a moment, okay? maybe many of you already know this, but let's do it to make sure you don't, in case you don't. Okay, so I can define, for example, an addition function. Okay, addition of natural numbers. Let's call it p for plus. Okay, p x y. I can define p to be sort of lambda x, lambda y. Now there are different ways to do it, and this is actually the content of what I want to say. Is lambda x, lambda y. Well, one way to do it is we recur on the second argument, maybe. And we say if the second argument is 0, then the answer is x. And if the second argument, let's look at the result of the recursive call that z, then we just say x plus the successor of y is the successor of x plus y, so inductively that's z, so it's the successor of z. Okay? And so you can check, okay, easily that if I run p on numerals, that's going to be the same as the numeral for m plus n. In other words, that it really, in that sense, it really will be doing addition. Okay, so that's the first thing I want to mention. Now, the second thing I could mention is that it was utterly arbitrary to work on the second thing first. And I could just as well have defined q to be lambda x, lambda y, well, pyx. I could have defined it like that. Or just spell that out if you want. Just p to reduce it and plug that in here, except you're now recurring on x instead of on y. The roles of y and x swap. Okay? And this also, of course, implements addition. Okay? So this is just a matter, if you've never seen a recursor before, you ought to play with that to make sure you're like good with how to program that, but otherwise I think it should be pretty obvious. Okay, so that's what's happening with like p and q. So the thing that I want to point out about this is that even though this is the case, you're not going to be able to prove, if I give you a generic x and y, and this is a distinguished, you're not going to be able to prove, I'll just write question mark, well, pxy equals pyx, which is actually qxy. That is pyx just by definition. So this will hold. This one is going to be problematic. So if you're not familiar, I need to emphasize this because it's an important transition point, right? If you're not familiar with working with what we've been doing so far, you might have been saying, oh, for God's sake, he insists on writing triple equals and he's muttering about something or other, but anyway, it's equality. Okay, so now it's time to wake up. Because actually, it's not anyway, it's equality. Because these things are not going to come out to be the same. Okay? That is, generically, these are not definitionally equal. Okay? Now, to prove that, that reminds me of another undischarged obligation I have to you. I motivated looking at proof terms by saying I was going to prove the disjunction property by analyzing proof terms. And I decided to put that in abeyance because I didn't want to get too involved in meta theory. And it would take me a whole week probably to develop everything. So I'm just going to hold that in abeyance. By a similar hand-wavy assertion, there are ways by meta-theoretic analysis to show that it's certainly with the beta rules only, that there's no way to fill this in, that this equation is not going to hold. But intuitively, what is going on? Well, the reason is that to prove an equation like this requires a proof by induction. And what does a proof by induction do? What a proof by induction does is it says, if this holds for every m and n in your sort of meta theory, that is, if you can show this is true for every numeral, then proof by induction says this holds generically. Or you can reverse it the other way around. To show something generic like this involving variables, you reduce it to showing it for all the numerals. Okay? And the principle of induction is exactly that. But the point is that the notion of definitional equality is a pure equational theory. And you don't get such a proof by induction. Okay? It's not around. There's no way to make the argument assume like p of xy equals q of xy, now prove something about px successor of y and qx successor of y. There's no rule like that. If you look at the rules I wrote down for definitional equality, there is no rule like that. So what you're groping toward, what I want to bring up here is that these are what you might call extensionally equal, which is equal in the usual sense of function equality, meaning they have the same graph. That is, or another way of saying it is, they have the same I/O behavior. For every input, they give you the same output. In other words,
if you run it for every numeral m and n, both of these guys are going to answer the same thing. And so we say the terminology is extensionally they're equal, but intentionally they're not. In other words, intentionally, meaning this sense of definitional equality, they're not equal. And what is that intentional or definitional equality? So this is also said, the terminology is also to say definitional. Okay, then they're not equal. I'm not proving to you that they're not, but they're not. Okay, so they're definitionally or intentionally not equal. So a way of saying that is they represent a different algorithm. Okay, so the idea about extensionally equal is in Frege's terminology means they have the same reference. If you know, for those of you who may know Frege's terminology, they have the same reference, but they do not have the same sense. So if they're not equal, then we'll say they have a different, and the Frege's terminology is sense. The sense is the means by which the referent is designated. So I'm expressing the same I/O behavior in two different ways. And so they have a different sense. That's the terminology. So if you go back to Frege's work on sense and reference, if I remember correctly, I'm doing this off the top of my head, he drew the idea about the morning star and the evening star. They both refer to Venus, but they have a different sense. One of them says you look a certain place in the morning, the other says you look a certain place in the evening, and we call that thing you see the morning star and the evening star respectively, but they refer to Venus. They're not even a star, but anyway, they refer to Venus, okay? And so that was I'm pretty sure that was Frege's original example. So they have the same reference, but not the same sense. Or we might say they have the same I/O behavior, but it's a different algorithm. Okay, that's fine. I think that's reasonable. Okay, so these are called definitionally or intentionally not equivalent, where they're extensionally equivalent. This distinction is important because extensional equality, I need to find a place to write this. Extensional equality is a matter of proof. So the idea is now I think I said something like this last time. The way we're setting this up is intentional equality is sort of analytic, is what the idea we want to have here. It doesn't require proof. Whereas extensional equality is synthetic, means it requires proof. And so in the case of the natural numbers object, this is very vivid, okay, because you must have a principle of proof by induction to prove the extensional equivalence of P and Q as I've given them here. Okay, you need to do an argument by induction, and so that means that there needs to be evidence backing up this equivalence, as opposed to you just declaratively or specify by this simple inductive definition of this binary relation of definitional equality given by rules. That is a relentlessly RE notion, right? You're just enumerating all the instances of it. But if you think for a moment about what extensional equality of functions is, the quantifier complexity of, let's say we have a type like this, n means nat now rather than right nat, okay. For equality here has very high quantifier complexity. You know, quantifier complexity. In other words, it's a bunch of nested for all exists kind of thing going on, okay. Whereas if I define this definitional equivalence just by enumerating the cases by giving you these rules, I'm defining something which is sigma 1. It's just it's a recursively enumerable predicate. And the equality that you would want, extensional equality, is not going to be RE. You get a very high so one way of saying that then is this distinction. Another way of saying it is proofs of extensional equality at higher type like this become complicated and require proof. Okay, so that's what's going on. So that's a distinction that we're going to draw. And this distinction is very important for what we're going to do next, because we now have to figure out, well, then how are we going to express this notion of extensional equality? So what I want to say is, so another way of saying it is that intentional equality
as I define it, is an inductively defined judgment. And the terminology that we get from Martin Luff is the terminology of a judgment. This is an inductively defined judgment. I gave a bunch of rules, which I've just now erased, the most recent ones, which tell us what it means for two things to be definitionally equal, whereas extensional equality is a proposition. So a statement like the one we have over here, Pxy equals, I'm going to Qxy, okay, I will write here in nat, like that, is a proposition. It's a proposition that requires proof. Okay, that is, we could potentially think about proving such a proposition, and we might, in fact, we'll end up in this particular case exactly saying that this is sufficient for that. And I'm going to actually work out how do we exactly say that, but that is what we're going to do. We're going to say that this is enough for that. Okay, so we'll say that in some way. But that's the notion of proof. The notion of proof is you need to prove this in order to prove that. Okay, so that's the idea. So this is a proposition. So it's an atomic proposition. In other words, it doesn't have any connectives involved in it. Okay, it's built up out of these two expressions. So more generally, we're looking at, for example, this is an instance of being equal m and n, any arbitrary terms. It's an instance of that being equal in nat. So the transition I want to make is this, is that by the propositions as types principle, which we're taking rather seriously, extensional equality in this sense, that's what I want to call it here, equality of reference, okay, extensional equality, is a family of types. That is, what we have is, for every x in n, that's the way I will write it down, every y in n, we will have that x equals nat y is a type. I could just as well have said prop, okay, because from my perspective, those are just synonyms, okay? It's just a way, you know, it's true I tend to have a somewhat propositional attitude toward this, but in a short while what I'm going to do is I'm going to undermine your tendency to think of this as a proposition which is somehow different from a general type, because the whole point about homotopy type theory is that the equality should not be thought of as merely a proposition, but should be thought of as a type. That's a significant technical point. But for right now, let's just like say it's a terminological issue. It's not really, but it'll turn out to be a mathematical issue, but right now it's a terminological issue. So I could just have called them props, or just as well call it prop or call it type. So the idea is that this is kind of saying for every x and y, this, you know, expression here, which sometimes for the reasons of just notational regularity is written identity xy. It's a little bit, things look better on the board if you do that. Okay, that is a type. So the idea is that a proposition, so it's a proposition, it's a propositional function actually, if you want to say that. It's a propositional function, two-place propositional function, otherwise known as a binary relation. That's really what I wanted to say. And that binary relation or two-place propositional function is a binary or two-place family of types. Okay, so that's where now the props as types principle starts to give us traction. Okay, because now we are saying, well, we have this notion of type around, and you know, depending on your particular like experience base, a lot of things work by having sort of data over here and propositions about them over here, and they're not mixed. So first order logic works like that. Higher order logic works like that. Okay, that's not strictly true about higher order logic. No, so well, never mind that. Okay, but first order logic works like that. Here we have a complete merger of the data aspect of things and the logic aspects of things are all the same. That's what's going on here.
Okay, so this is the idea of a family of types. Now, the significance of having a family of types like that is that I can instantiate by substitution. So, for example, it follows from this fact, okay, so let's call that star. So from star, we obtain, for example, anything you like, we obtain the following thing, that id A, let me write it like that, Mn is a type whenever M and N are in NAT. Okay, that's the idea. So I have a family of types indexed by these variables. I can plug in for the variables and obtain instances of that. And that is an honest-to-God type, aka proposition. Okay, for right now, as I say, I'm being loose about that. Okay, so it's a type, which is also known as a proposition, expressing the equality of M and N in type A. Or this should have said NAT. It's in general A, but in the particular examples I'm doing, it's NAT. Sorry. Okay, so we'll do that with NAT. So there are other such things. Another example, which sounds, so this is the premier kind of motivating example. But another example is more, that feels more like data, is I could say, given X and a NAT, I will have a family of types. Let's call it seek. Let me write it with a capital to try to be consistent. Seek X is going to be a type. And I will think of this as the finite sequences of NATs of length X, which is, of course, a NAT, as we say here. In other words, associated to each natural number is a type of sequences of natural numbers of that length. Okay, that is another example that comes up a lot, like in programming languages. Now I want to come back to the remark I luckily didn't erase. It was about to erase. It didn't erase. Is that we look at this as so this brings up an important point. Okay, so we can observe now the following fact. If we take something like seek, I could do the discussion also with identity, but I just felt like doing it with seek. If I take something like seek and I look at, for example, PMN, and I look at seek of QMN, as I called it like that, well, when they're given as numerals like this, I will claim that these things have the same sense. They are definitionally or intentionally the same type. And the reason is for the fact because PMN for numerals is definitionally equal to QMN. When you start using proof assistance, if you do that for type theory, the thing I'm discussing right now will bite you in the ass over and over and over again. So that's why I want to bring this up, okay? And people find it annoying, but the best I can do for you is explain to you why things are the way they are. And then we can discuss whether they could be better. That's a separate issue kind of thing. But let's just say this is why they're the way they are. Okay, so we have this fact, but, and this is the thing that is extremely annoying, if you have around variables like X and Y, it's a real question, what should be the relation between, just using my running example, I'll just write versus, in that context, QXY. Okay, so the question is, what should be said there? Okay, what should the relationship here, well, what is it and what should it be? Well, they're not going to be definitionally equal for the reason that I mentioned before. Because these are different algorithms and definitional equality is expressing equality of sense. So this type is sort of presented to us, one may say, in a different manner than this type is presented to us, and you notice that fact. That's a definitional equivalence. But surely there must be some relationship between them because you reason quite naturally. Anything I could plug in here, I could also plug in over here. Right? Well, why would that be? Because, well, your argument is if I take x and y to be any numbers in particular, like we did in the previous line, and I take any element of Pmn, since Pmn is Qmn, then of course that element either is in here or can be regarded as being in here using some kind of coercion or retyping or some words like that. And that's a very reasonable intuition, but and the question is how to make sense of that, okay? So the way to make sense of it, to broach a subject that will come up later, is we might argue, the first thing that we might argue is that, well, at the very least, so they're not definitionally equivalent, but we might say that they are isomorphic. But this is going to raise another topic, so that's why I bring it up. Okay? You can say they're isomorphic. So you might say, well, all right, in some sense, to be made precise, these should be equivalent. So I'll use a notation that is alien for the purpose of making my discussion. So there should be some equivalence between these two things, which is expressing some notion of isomorphism. But what does that mean to be isomorphic, or what does that mean? Well, what it ought to mean is something roughly like, I can say that A is somehow equivalent to B, should mean that I have a way of sending everything in A over to B, and I have a way of sending everything in B over to A at a minimum. But of course I would like it to have some properties. So I would like, for example, if I send something over to B and send it back to A, maybe I should get, oh boy, this is annoying, I should get the same thing back, whatever the same might mean. Okay, and if I send something to B, oh, which way do I want to do it? No, first of all, if I send something from B to A and then send it back to B, maybe that should be B. But you see, I'm chasing my tail a little bit because I don't know what I mean by equality here. All right, so that's a question to be worried about. What do I mean by these two things being equal or not? Okay, and well, suffice it to say, for the time being, expecting this to hold definitionally is much too strong. Okay, so what we're going to use is a propositional equality. So these should be propositionally equal in A, and this one is in B. Given I'm foreshadowing everything I'm going to develop, but that's the gist of it, right? So this will say, oh, but what does that mean? Well, you see, that's a type. So it really means there ought to exist some data, which is a witness to that fact. That is a proof of that thing, and some data, which is a witness to that fact, which is a proof of that thing. Okay? So what we're having here is a picture that says, I sort of have like one way of staying, one way of staying at A is the identity. I don't do anything at all. It's always hard to draw the identity because it's the one that doesn't go anywhere. And then I have this other loop, right, which in this case is G after F. And I want to know that these two things are somehow related to each other by this alpha. Okay, that's what is being expressed here. Okay, that's the kind of thing that I want to say. It's really not alpha itself. This would be alpha sub A, and this would be beta sub B for the particular element, and then alpha, let's say, is in general for all of those. So I would want to have some relationship. So the picture is that I want to have that alpha is somehow saying something about G composed with F being equal to the identity at the type A arrow A. That's the kind of thing that I'm looking at. Or we could write A arrow A down here if we want. There's different notational conventions. Okay, so we want to say that. So what I'm broaching for you now is this idea that what we're doing is we're saying there's some kind of map between these maps which says that they are equal, because this equality wants to carry with it the force of this movement that is saying that if I go around this loop and go around that loop, it's the same thing. That's what's being said here. So that's one possibility, is that this is a little bit loose. Obviously, it's very loose right now, but this is foreshadowing what I want to explain. So this will eventually be called the notion of equivalence. It's going to get a little bit more complicated, but we call this equivalence. So isomorphic, aka isomorphic, is going to be a special case of a general notion of what we'll call equivalence. Okay, of these two things. But you might also expect that in some sense, those types not only should be equivalent, but should be equal. And what would that mean? Well, one thing to say about it is to say that, well, two types are equal exactly when they're equivalent. That's a possibility. And so the univalence axiom, which I've alluded to several times, has as a consequence, it's actually a little stronger than this, but it has as a consequence that the equality of A and B is the same as the equivalence of A and B. Okay? So that's what univalence is all about. And that way, if I have such an equivalence via univalence, I can regard them as interchangeable in all contexts. Now, to make that precise, though, requires me to tell you what does it mean for A, what sort of animal is A equals B, okay? And what sort of animal is A equivalent B? Because, you know, we're in a game where everything is in type theory. So this ought to be a type, and that ought to be a type, okay? And then the univalence axiom will tell us that these two types are equivalent. That's the actual univalence axiom. So we'll get to that a little bit later, because you have to keep remembering that whenever I write something down that seems sort of propositional, like expresses a relation, what I'm really writing down is a family of types. And that means it has inhabitants, it has structure, and these two families of types are related by some information that expresses that structure. So that is the beginnings of like where this whole discussion of equality goes. Okay, good. So I wanted to make sure I said something about seek. Yeah, okay, so now I can start talking about the setup. So this kind of thing can be very annoying, okay? And I'll explain where that annoyance comes up now. Let's start developing the theory. I need to get a drink of water, so let's take a very brief break. I'll be right back. Okay, so now let me say a little bit about the formalism of dependent types, and that'll be enough for this week. Okay, so now let's set that up. So questions so far? I know often when I'm writing at the board, I end up staring at the board and I don't notice if you have questions. Yeah.
But if you, okay, so if the sequence is actually a cluster, then it will preserve the path, like the identity.
Yeah, so I haven't like gotten far enough along to yeah, and that's what will induce that equivalence, right?
But in
Yeah.
that case, you don't need univalence to prove property.
Oh, that's true. What the univalence is about is to say they're equal. In other words, that having an equivalence gives you a equality. Maybe I don't understand your point. Oh, I should.
You can directly prove equality without using in this space.
Oh, yeah, okay, maybe in this case.
But it will be useful in other places.
Okay.
In this spatial space.
All right, it's a little technical point for now. I'm trying to motivate the subject, so let's come back to that. Is that okay? Okay. Okay, so other questions? Okay, so now let's just put in a discussion now of, let's start talking about the structure of dependent type theory. Some of you may know this already, but I want to mention a few important like general properties about it. So what is the general setup? Okay, I'll call it the sort of the setup for dependent types or families. So dependent types is basically a synonym for families of types. So the central notion in dependent type theory is the notion of a family of types. So you can see, like from the examples that I used, I have now the notion. So implicitly, what I had previously, let me write it here. Before I got to dependency, I had a judgment A as type. And I did not need any judgment. There was no need for any kind of judgment A is definitionally equal to B. That didn't come up at all. Okay? And then I had M is of type A. And then I brought up the notion of M is M prime in A, definitional equality. And I brought that up kind of out of nowhere. Okay? Because I just said, well, Gensen studied this thing, and I started telling you the story. I had a reason, which was to say that whereas in sort of so-called simple type theory, this is in some sense an independent subject, like I can perfectly well define you what the types are and what their elements are, and I never need to mention this in order to make that definition. And then I can talk about when they're equal. With dependent type theory, they're all intermixed. You can't separate them out. So what happens in dependent type, the structure in dependent type theory, is we get this. We get, first of all, what are called the context or closed types. So we have judgments, gamma as a context, and we're going to have a judgment gamma equals, definitionally equal to gamma prime. So that's one setup. Then we're going to have the open types or families, which is in a context gamma, A is a type. And in a context gamma, A and A prime are definitionally equal types. So that's a setup we need. And then the third thing is we need the elements or objects or whatever of types. So these are M is in A and M is M prime in A. Written like that. So this kind of looks familiar, but unfortunately it's for a different notion of type and a different notion of context. So although they look the same as what we had before, they're not exactly literally the same. I have to now tell you what these are. So I want to give you the architecture of this and show you how these things fit together. So there's no good way to start because everything, they're all defined simultaneously. So wherever I start is, I'm going to be chasing my tail. So I'll start somewhere. So what we'll have is this, so we'll have the notion of an empty context. That'll be one way of forming a context, and then now the games begin. If I have a context, and relative to that context I have a type, then I can form another context with a variable in it, like that. Okay, so that's another context. So this is a little inductive definition that builds up contexts from types that are indexed by the preceding variables. This allows me to do things like consider x in nat, y in seq of x, and then in that situation do something involving x and y. The point being that the type of y depends on the variable x that occurs in front of it. So they're not given independently, they're given rather dependently. So that will then give us some minor headaches. Okay, and then the notion of definitional equality. Since I'm not going to do meta theory, you'll thank me, I don't need to, there's a lot of things I can be kind of loose about here, and I can write them out. Then so those are definitionally equal. It's just point-wise definitional equality. Okay. The critical thing, these things get defined when I define particular types, which I'm going to hold in abeyance for the time being. But one thing I can tell you, even before I tell you what types exist, I can certainly tell you what some terms that exist. So let's jump to there. So I can say the following. If I have gamma xa delta, then x is in A. That's one form of term.
In the previous rule, how did you know it was okay?
Did I make a mistake?
No, it's fine. But how did you know it was okay to compare them in gamma?
How did I know what?
That you could compare them in gamma instead of gamma prime?
Oh, yes, because there's going to be, this is the thing of where do I write everything down. Somewhere or other I'm going to write down that if gamma is equal to gamma prime and you can get gamma from A type, then you can get it from gamma prime, and the same over here. there's no good place to start. Okay, the only way to do this is you have to say everything simultaneously. You can't say it anything you say sequentially involves a forward reference. Okay, so all right, so I'll do that. So here's the notion of a variable. So this corresponds to, you'll notice, to the reflexivity principle, structural property that we talked about for entailment, because read as an entailment, it's A entails A. There's one little thing that should make you suspicious, though, and I can mention this right away. Did anybody notice that there's something suspicious about this? Semi. Well, you're very experienced. Okay. Anyone besides Favonia? Admittedly, I'm in the middle of presenting everything, so it's hard to say something completely accurately, but there's something that you might have noticed already. No? When I form this context, if you crank out these rules, what I will know is that A is well formed relative to gamma. So here, A will be well formed relative to gamma. But then, over on the right, I'm using A in the presence of delta. So there's implicit use of weakening here. Okay? So there needs to be an idea of weakening that says, it could be written like this. Again, which rules I write down in what order is utterly arbitrary because there's no order, okay? So I'll just write this one down. And I'll write J here for any of these judgments on the right. And if X is, if A is a type here, then I will just assert that you can stuff a variable in the middle and still get J. And this is weakening. So implicitly here I used weakening because really what I'm getting is X is of type A relative here, relative to gamma, and then I have to weaken A beyond itself and beyond delta in order to put it over here, because now it's sitting in the context of X and all the things in delta. So you need a principle of weakening. So that's a very subtle point, but when doing meta theory, not so much for our Blackboard purposes, but for when doing meta theory, that kind of thing can really bite you. Okay, and so I will leave as an exercise. Consider what you should say about exchange and contraction. But there should also be a principle of substitution. And again, we'll write it like this. So we'll say, let's write it like this, and then I'll write J here. And I will say, if M is in A, this is like a Blackboard convenience by quantifying over J here. You have to know what I mean. What I mean is, for each of the judgments that I'm taking over that could be here, state this rule in the obvious way for each of those choices of J. So this is like a cheat that I'm doing here. All right, so, and now here's the tricky thing, because this is the thing about dependency. You have to substitute in here, and well, also in here. Okay, so this is substitution or instantiation, depending on your point of view. It can be written like that. Okay, so that's telling us that, so this corresponds to transitivity that we talked about as the structural properties of entailment, because it kind of says, you know, if all this stuff plus A entails J, and you know A, then all the stuff without A in it entails J with the lemma, so to speak, inlined. So that corresponds to the transitivity of entailment. It's a more general form of it. So these are the structural properties then. We have reflexivity, weakening. I left you to consider exchange and contraction, and transitivity or substitution or instantiation. Now we have some other ones that are also a little painful to write out, but I will do it I'll do some examples, which are what are called functionality rules. And let me not use this meta convention. So let's say we have n is in B, and we know that m is equal to m prime, let's call that, in A. Then I wish to know that, well, we're going to have an issue of an arbitrary choice here, but I'll just do it. And the thing I want to do here is say n is functional in its free variable, x, that I've designated, and this will have to be instantiated, again, arbitrarily, and it's going to raise a question, which is why I bring it up, okay, which looks like that. Okay, so if you squint, like as a first cut, suppose there's no delta, and suppose b doesn't depend on x, then you would erase all this and you would say m for xn is definitionally equivalent to m prime for xn in b, in that particular case. So that's like a nice special case, okay? The general case, I think, looks like that. And this is called functionality. And the same holds here. This is where, is if I have b as a type, then what I would write is m for xb is the same type as m prime for xb, definitionally. So that's kind of like two rules in one. So these are the functionality principles. So this says that the type families have to respect definitional equality in their free variables. You're not allowed to distinguish seek of 3 plus 2 from seek of 2 plus 3. You're not allowed to distinguish those because 3 plus 2 and 2 plus 3 are definitionally equal, so you can't distinguish them. So this is that's what this is saying. You can't treat one differently than you can treat the other. Oh, what do I mean by that? You can't treat one differently from what you do the other. Well, what I mean by that is they classify the same expressions. So another rule that pertains to all of this is if m is a and a is a prime, then m is a prime. Okay? And similarly for definitional equality, if m is m prime in a and a is a prime, so this is quite important, proves m is m prime in a prime. So in other words, definitionally equal types classify the same things. You can't have an element of seek 2 plus 3 that isn't also an element of seek 3 plus 2. Okay, they have to be the same. Now, for instances that are not definitionally equal, then there's something to be said, but that's what I'll get to, okay? But right now, this is the setup, okay? So we have these kind of judgments. So these are the respect for type equality. Then I want to make sure I say everything I need to say. Weakening contraction, yes. Okay, so I think I said all that. Okay, and there's a few other rules which I'm not going to write down here, and you can look them up. So to see the general discussion, look at the Nordstrom Peterson Smith volume. I think the book, I think 90 maybe question mark that I put on the course page. Okay, there's a lot of discussion of that, and there's also a 45 or 50 page paper by Martin Hoffman called Syntax and Semantics of Dependent Types. Syntax and semantics of dependent types. And if you look in the appendix, the hot book appendix, there is an appendix written by Carlo that will also give you a summary of these things. Yes? That's wrong?
The second appendix.
What's that?
Section 2 of the appendix.
Oh yes, hot appendix part 2. So part 2 is the, yes. Yes, you're right. Let's not go there. Okay, yes, hot appendix part 2. You might ask, why is there part 2? Well, because there is. Okay, so part 2 is what Carlo wrote. Okay, so you can look there. So, because I'm not going to be doing meta theory, so I don't need to be ultra precise about exactly what are all the rules. Okay, I want to just like give you some of the rules. Okay, to point out some like main issues. Okay, good. So now we can start talking about populating the type theory with particular types. Okay, so motivate, yes.
So the structural rules that you wrote up, so for IPL, we said that most of them were admissible. I mean, you need
Yeah, so that's the issue of meta theory. Okay, so There are many ways that are subtly different to write down the actual official defining rules of the theory such that the various structural properties in various forms are admissible or not, or are written explicitly as rules or not. And this is a whole big enterprise unto itself. But it mostly pertains to doing meta theory, like when you're trying to prove something about the theory, like for example that every well-typed term has a normal form or something. Then you need to know exactly what all the rules are. For my purposes, let's just say the various structural properties must be valid. These must be valid, okay? You can arrange them to be admissible sometimes by building weakening into all the other rules. There are various tricks you can do, okay? And I don't really want to, if I were doing meta theory, I would have to be like really particular about all that, but I don't want to be too particular about that. I'm pretty sure I don't need to be too particular about that. So we could just think of these as all rules of defining the system, and I'm not going to worry about which ones are admissible or not. Yeah. Okay, that's a rule of thumb-ish way to think about it. It's good. Okay. All right, does that make sense? Okay. All right. So good. So let's look at the identity type just to get going. So we'll have this ID. So we now have rules that look like this. We have what are called formation rules. Now, there's another issue is going to come up very shortly, but we'll for right now, let's work like this. So I will say the identity at A, M, and N is a type. That's called a formation rule. If A is a type, and M is in A, and N is in A. So this is called, the id formation rule. Okay, written like that. Okay, so that just says you can form the type that expresses the equality of M and N and A. Okay? And then I will mention something as an aside, is A could, in fact, usefully be another identity type. Because, okay, yeah, that's obvious in some sense because it can be any type. But it's actually very interesting to look at types that look like this, the iterated identity types, where what we're doing is, I'll write it like this. I talked about alpha and beta being proofs that M and N are equal in A. One can then also talk about those proofs being equal as proofs of such equations. And that's an iterated identity type. And in fact, I can iterate that further, okay, as much as I like. So this goes to any dimension. In other words, I can iterate that and talk about if I'm going to have a proof of the fact that these true proofs are equal, and then I can ask whether those proofs are equal. And of course, that will have a proof, and so on. So this will lead to the idea that maybe I'll talk about next time, that the identity type presents the structure of what is called an infinity groupoid. But before I do that, let's look at the identity introduction. So what is the identity introduction rule? When can I form a proof of equality of two things? Well, the most obvious thing to say is if it's going to be an identity relation, it surely should have a proof of the fact that things are related to themselves. Everything is equal to itself, and we'll call that maybe refl A of M. That's a common notation, okay, saying that that's a witness. This is a proof object, or witness, people use different terminology, expressing the fact that M is equal to M, okay, in the type A. All right, and then that's identity introduction, and then I'm going to leave you, oh good, perfect, Penelope, what is it called? The cliffhanger, here I'll leave you with a cliffhanger, which is the evil villain has tied the girl to the railroad tracks. All right, and now we'll see what happens next week. Okay, so come back next week and see whether we can save the damsel in distress and fill in the identity elimination rule here, figure out what that should be. And that will be the beginnings of us talking about equality and dependent type theory. Okay, so good. So that's good timing. All right, so let's stop there. Okay, thanks for your attention.